Welcome to video 16 on the TTB course. This video is from part 4 of the course. In part 4 we consider techniques for monitoring TT systems. In this video we consider ways in which we can make best use of an internal watchdog timer in a TT system. The material in this video is based on Chapter 16 from the ERES2 book. If you have not yet read Chapter 16, I suggest you stop the video, read the book chapter, and come back and watch the video again. Let's go right back to basics. Suppose there's a hungry dog guarding a house and someone wishes to break in. If, during the burglary, an accomplice repeatedly throws the guard dog small pieces of meat, then the animal will be so busy concentrating on the food that he will ignore his guard duties and will not bark. However, if the accomplice runs out of meat or forgets to feed the dog for some other reason, the animal will start barking, thereby alerting the neighbours, property occupants or police. That's the starting point for a watchdog system. Watchdog timers in a microcontroller typically operate as follows. The timer must be refreshed at regular, well-defined intervals. If the timer is not refreshed at the required time, the dog will bark. In other words, the timer will overflow, a process which will usually cause the associated microcontroller to be reset. When starting up, the microcontroller should be able to determine the cause of the reset. That is, it should be able to determine if it's been started normally or restarted as a result of a watchdog overflow. If the microcontroller has been started as a result of a watchdog overflow, we can then react to the watchdog overflow in an appropriate way. This might typically mean shutting down the processor as safely as possible in which the watchdog overrun occurred. It's important to appreciate that if we can't distinguish between a normal power-on reset and a watchdog reset, then we may end up putting the microcontroller through a sequence of resets, continual sequence of resets in the presence of a sustained fault. This can be very dangerous. So let's consider what the purpose of an internal watchdog timer is in a TT system. All of the TT designs that we consider in this course incorporate some form of scheduler on each processor. We use a watchdog timer in such designs to detect situations in which the scheduler is not operating correctly, and to help move the associated processor into a fail-safe state in these circumstances. That's our key use for a watchdog timer in the systems that are considered on this course. So let's consider the required watchdog timer characteristics and the required watchdog timer settings, plus the need for power-on self-tests and built-in self-tests on the watchdog component. So these are our required watchdog timer characteristics. As we've touched on previously, at processor startup, it should be possible to determine whether the watchdog timer caused the reset. I see this as an essential characteristic of watchdog timers for use in reliable embedded systems. The watchdog timer should be driven from a clock source that is independent of the source that drives the scheduler. As we've discussed, our main use for the watchdog timer will be to detect that the scheduler is not operating correctly, so we need to use a different clock source for the watchdog timer than the clock source that we use for the scheduler. Again, I see this as an essential characteristic for the watchdog timer. Once it has been started, it should not be possible to disable the watchdog timer. Again, this is obvious if we have coding errors, for example, in our system, and it's possible to disable the watchdog timer, then that will leave our system rather vulnerable. So I see this again as an essential characteristic. Where possible, we'd hope to make it impossible to change the watchdog timer overflow settings once the watchdog timer has been started. This isn't essential, but it is a highly desirable characteristic. For example, if I've set the watchdog timer to overflow after 2.5 milliseconds, I hope to have that value locked down so that I cannot change the value while the system is operating. It's not always possible to obtain this behavior in the majority of processors. A windowed watchdog timer is also a good solution. In a windowed watchdog timer, we check not only we set a watchdog time, for example, of 2 milliseconds. We check to make sure that the watchdog is refreshed within an interval of 2 milliseconds, but we also set a lower bound on the refresh rate. So if someone attempts to feed the watchdog timer every 1 millisecond, this might be considered to be too fast. We might set the window so that the watchdog timer must be refreshed no more frequently than once every 5 milliseconds and no less frequently than every 10 milliseconds, for example. That's a windowed watchdog timer. Again, this can be useful, but it's a desirable characteristic rather than an essential characteristic in most of the systems that I develop. So we will typically use an external crystal oscillator as the clock source for the scheduler, and an internal RC or similar oscillator to drive the watchdog timer. The stability of RC oscillators is comparatively limited. This means that we can never expect to use very precise timeout limits. We typically set a watchdog timer timeout of around 2.5 ticks and feed the timer at the start of each tick. So we're not attempting or expecting to have very precise control of timing as a result of the watchdog timer. When we want to do things such as monitoring the execution time of tasks, processes we'll consider in later videos, we'll use more precise timing mechanisms to allow us to do this. The watchdog timer is there primarily to ensure that the scheduler is continuing to operate correctly. If the scheduler doesn't operate, the watchdog task won't be released, and we will pick this up within around 2 to 3 ticks. During startup tests, after we've performed the necessary low-level CPU checks, we would expect to test the internal watchdog timer. Having confirmed that the internal watchdog timer is operating correctly, we will then use this timer to test the scheduler. Further periodic tests of the watchdog timer are also likely to be required during the system operation. This is particularly important if you only have a single processor and if you're relying on the watchdog timer to check that this processor is operating correctly. The table below shows some of the diagnostic test interval figures that you may wish to use to determine how frequently you check your watchdog timer in different platforms. You can find some examples of mechanisms for performing power-on self-tests and built-in self-tests that include tests on the watchdog mechanism in TTRD2 19A. You'll find that TTRD, that time-triggered reference design, on our website. The key point to note from this slide is that if we're using a watchdog timer, we need to consider what posts will be performed to ensure that the watchdog timer is working correctly, and we need to consider what built-in self-testing may be required to ensure during the system operation that the watchdog timer is still operating correctly. That brings us to the end of this video. Before you continue with the course, please read Chapter 17 in the ERES2 book. Thank you for watching.